our solution of the problem smoke stream. At first, I'll remind you problem definition. A glass jar is covered with cellophane. A 10-folded paper tube of length 4 or 5 centimeters is inserted hermetically into the jar through the cellophane cover. The tube is oriented horizontally. If one burns the outside end of the tube, the dense smoke flows into the jar. Explores this phenomenon. But first, let's make a plan of our work. The first point in our plan is explanation of our phenomenon. I'll explain you the basic physics of this phenomenon. Then I'll make some theoretical model, explain you influence of the jar on this phenomenon, then investigate this phenomena on different parameters, and make conclusions of my work. But first, let's see of the smoke formation. When we burn outside end of the tube, some temperature gradient occurs. It looks something like this. Near the flame, there are burning, and where the temperature is lower, it is here. There we have a bit lower temperature, and this temperature not enough for burning. That's why thermal decomposition takes place. It's named like paralysis. Then, at the end of the tube, the temperature of our smoke is larger than temperature of outside air, but the density of smoke is still larger than density of air. That's why it has a negative balancing. Why does smoke move through the tube? Here we can see the experiment with Scotty tube, and you can see how the smoke moves through E. Why it is so? You can see that at first smoke moves up. It is because there are hot air streams that push our smoke particles into the jar. And that's why, because of the thermal expansion that takes place, we have motion of smoke through the tube. We don't see any smoke outside the tube because of there are enough oxygen to burn outside layers of the tube. Yeah, though inner layers is burning in lack of oxygen and paralysis take place. Let's see about some basis of our theoretical model. Here we consider that acceleration of our smoke stream is very small. That's why we can consider that pressure inside our tube is almost constant. Here we have heating of gases that we have in our tube. Here we have cooling of our tube, and we also have cooling through the paper. And also for simplification, we took that all gas in our tube have the same temperature. I mean the gases that forms due to paralysis. Now we considered our smoke stream at first like piston, and this piston have some edge, and this edge move with some velocity. It is so because of expansion of our piston. And by what we can have changing of volume of this piston. It is because of formation of new gas due to paralysis and burning, and due to thermal expansion of all gases that we have in our tube. And from calculation of this changing of volume, we can calculate the velocity of moving of the edge of the tube. Here you can see the formula for this calculation. T1, T2, and T3 is some constant coefficient that we can't calculate from theory. It is from experimental data. And we can't say about numerical data of velocity, because we can only say about the form of dependence. Now let's consider the trajectory of the stream. In ideal case, it should be ideal parabola, but in our case, it is not ideal. Why it is so? What is the reasons for the trajectory current? It is so because air drag. We also don't don't obtain ideal parabola, and the end of the tube that in the jar, it is heated. That's why convection in our jar occurs. That's why with these convection streams moves our smoke stream. That's why trajectory is also curved. Now let's see our experiment on the open air. As you can see, smoke moves down, but the smoke stream is very unstable. It flows out with air flows, with different flows of convection that occurs when we burn. And let's see what we have in our experimental setup. Here you can see our vessel that was covered by cellophane, and tube was put into the jar and was fixed by 2 elastic bands. And now let's see how our experimental setup is formed. As you can see, the trajectory of the smoke is quite stable because there are not many air flows inside our tube, except for small convection streams that occurs because of heating of the end of the tube. Now let's consider smoke motion state. The first stage, and when we don't see any smoke outside the tube, it moves inside. And then we have appearance of the smoke. When bottom part, lowest part of our stream touches the bottom, we have some laminar flow of our smoke stream. And there is a moment of increasing velocity when trajectory is also increasing. And we have a moment of stationary velocity when trajectory is quite stable. But when the length of the tube is very small, the turbulence occurs and the smoke stream moves up. And we considered only 2 of these motion states. It is appearance of the smoke and stationary velocity. Now let's see the variable parameters of our setup. It is inner diameter, length of the tube, number of layers, length of the tube part in the jar, kind of paper, and of course the volume. Here you can see the photo of our tubes. We made about 400 tubes for this setup, and all of these tubes have been burned. Now let's see about influence on the inner diameter. Because of the projector, we can't see this smoke stream because it is very thin and have a very long density. But this smoke stream is visible quite well. Now let's see what will change with increasing of diameter. With increasing of diameter, velocity of burning, velocity of smoke stream, density of smoke is decreasing. Because density of smoke is decreasing because we have enough oxygen to burn full our paper. But there is interesting thing that we have. There is no smoke outside the tube with diameter larger than 1 centimeter and length of the tube less than 5 centimeter. Now let's move to another parameter. It is influence of the tube length. As you can see from this video, almost nothing changed in trajectory and velocity of our stream. The only thing that changed is time of observation of our phenomena. But if the length of the tube is very small, the turbulence occurs, let's say, is the beginning of my presentation, and smoke stream moves up. Now let's turn to the next parameter, is layers number. Here you can see velocity of the smoke and velocity of the flame. Here you can see the approximation from the theory. In our theory, we predict that this dependence should be hyperbolic, and as you can see, approximation is quite well. And you can see the comparison between different layers number. As you can see, here we can more thin stream and less dense. And now let's see what will change with increasing of layers number. The velocity of inner layers burning, the velocity of the smoke stream, and density of the smoke. And of course, the stream diameter is decreasing. As I told, it is because of velocity of burning. It is the most main parameter in these problems. Now, let's move to the next parameter. Is length of the tube in the jar. Here we can see the maximum deflection of beginning and the most curved part of our trajectory. And as you can see, this dependence is growing. This line is only qualitative approximation that with increasing of tube part in the jar, we have increasing of deflection. And as you can see from these photos, the deflection for the largest part, tube part in the jar, is more than the smaller one. And now let's consider influence on the kind of paper. We use 3 different types of paper. It was usual office paper with linear density 18 grams per meter squared. We use more thin one, which is 14 grams per meter squared, and the more thick one. It was a photo paper with density 200 grams per meter squared. And really, the changes was really great because with different kinds of paper, there are different nature of burning. Now let's move to the influence of jar volume. And we took a very small one, and as you can see, that nothing changed. We have the same trajectory, and I said that nothing changed. Now let's try to conclude. Smoke is formed because lack of oxygen. Smoke is pushed into the jar with hot air streams. Density of the smoke is larger, that's why it moves down. Curvature of the smoke motion the same on the jar or in open air. And also you can see that with increasing of inner diameter, place number, density of the smoke decreasing.
Now is the time.
And the decreasing.
So last time or no?
And the last thing I want to say, no smoking. Thank you for your attention.
Okay, now I have the time for the questions from the audience.
Okay, so my first question would be, why do you think that the pressure is constant inside the tube?
We think that acceleration of our somewhere was acceleration of our smoke is very low. That's why forces that acting on our smoke stream is low too. That's why pressure it depends on the forces. That's why it's very low, and we think that pressure is constant.
And why do you think that temperature should be constant inside the tube?
I don't tell that it should be constant. There is some distribution of temperature, and for simplification of our model, we took that it is constant, but it's changing in time.
Okay, and how did you measure the speed of the stream?
Okay, it's very interesting question. We took a video of our model, and from the movement of trajectory to horizontal part of movement. At the beginning of our process, as I told.
And does the stream expand when it flows outside of the tube?
I don't think that it is so, because the temperature is not low, to not change its diameter, but we took the age of our smoke stream to make more precise measurements.
And what was your final conclusion? Was the stream turbulent or laminar? The stream itself, is it turbulent or laminar? Because you didn't make any conclusion about this.
From the beginning, the flow of our stream is laminar. Then, when the length is growing, the flow of the stream becomes turbulent.
Okay, thank you. And now I have the time.